So for the last time of the afternoon, we welcome Romain Michon. Romain Michon was a student of Saint-Etienne University some years ago in musicology. He do Erasmus year in Ireland with Victor Lazzarini, and now he's finishing his PhD at Stanford University. So he has two talks now. I let you speak about that.
Thank you, Laurent. Well, yeah, I'm very happy to be here. So I'm just back home. I had to take a lot of exams in this room, so it brings back some very bad memories, but here I am. Okay. Well, hi, everyone. I'm going to talk about two different things in a row, so it's going to be two different talks, but the first one is going to be about faust2api. Which is a comprehensive API generator for Android and iOS. And you'll see very soon that this title is actually wrong because thanks to Stéphane, things got very recently extended to more targets than Android and iOS, and you can also do Juice and most of the Faust targets as a matter of fact. So I will start just by saying a few words about mobile devices and music. So mobile devices have been used as musical instruments for many years now, about 10 years. You know, so behind me you see a bunch of projects from many different people who've been using, who are kind of famous to some extent, you know, and who've been using mobile phones as musical instruments. So here we have Ga Wang, who founded the Stanford laptop orchestra that we see here. Guy is also famous for creating Smule, which is a company that makes musical iPhone applications, and he's kind of the first one who really used mobile phones as musical instruments and brought that to a more general audience. Here we have older stuff, as you can see, where here they were just using PD on this pad. Here, some antique smartphones augmented with some kind of very antique Arduinos, because those Arduinos are pretty old, you know, and so people have been playing around with those kinds of things for many years. And more recently, here on the top right, there's this app called GeoShred, which is using Faust internally to synthesize physical models of different electric guitars. Maybe if we have time left at the end of this presentation, maybe I can tell you a little bit more about this, because it's a pretty cool app, even though it's not really open source. But all that to say that those different tools are making music, and this one is using Faust. Okay, so. Implementing real-time digital signal processing engines from scratch on mobile platforms can be hard using standard audio APIs provided with common operating systems. So those of you who've been using Core Audio probably know that, you know, and Core Audio is actually kind of the easy one if you want to make audio engines for Android. Things are even more complicated because part of your application has to be in C++. Most of the graphical things are happening in Java, you know, and then this kind of adds all this layer of complexity, which you don't have on iOS. But the bottom line is those things are not always so straightforward and are pretty low level, and it's just nice to have access to something that is a little bit higher level to deal with audio on those different type of devices. So, well, just to extend maybe a little bit more on that, you know, there are tools that are currently provided to solve this problem, and I'm, for example, thinking about Juice, which allows you to now make iOS and Android applications, which gives you access to this very nice high-level layer, you know, to access the different audio audio facilities of your device. You know, another one which is not open source is, or maybe actually it is super powered open source. I don't think it's open source. Yeah, I think it's like half open source, but super powered is another one, you know, and to some extent it's a little bit like Juice, but it's older than Juice, you know, and it's really targeted towards mobile devices, which is not really the case of Juice, which kind of targets everything. At a higher level, there are different tools that are kind of similar to the one that I'm going to present here, and the main one is libpd that people have been using in this community for many years, you know, where you just can convert a PD patch to something that is embeddable in a mobile phone or into something else as well. And a student of Victor also did something similar for C-Sound, and I think it's called the Mobile C-Sound platform. Anyway, so on the Faust side, we had tools and we still have tools to generate Android and iOS applications from scratch just using Faust. You know, so you can write your entire app just in Faust, and then Faust to Android and Faust to iOS just allow you to convert your Faust code into a fully working standalone application. And those things have been around for many years as well. I think Faust to iOS is about 5 years old, and Faust to Android is a little bit more recent, but it was written 4 years ago as well. You know, so those things have been here already for quite some time. Okay, so today we introduced faust2api. So faust2api offers the same type of features on Android and iOS, as well as other targets, because I'll be talking about it a little bit later in this presentation. It's just that when we wrote the paper, the other backends were not implemented, you know, but now they are here, you know, so I'll probably extend to that towards the end of the presentation. But faust2api has Polyphony and Midi support, so everything you write with faust2api can be polyphonic and can be controlled by different Midi devices. You know, so if you plug a Midi keyboard to your device, iOS or Android, you know, you'll be able to control the synthesizer implemented in Faust in the audio engine. There's separate audio effect chains that can be coded in a separate Faust file, which is very important, because if you make a polyphonic synthesizer in Faust, well, you kind of don't want to have the audio effect to be in the same file than the audio synthesizer if the audio synthesizer is going to become polyphonic, right? If you have a reverb applied on your sound, you only want to have one reverb for the entire thing and not one for each voice that you're allocating. So it's pretty important to be able to separate those two things. So faust2api allows you to have a Faust file for the synthesizer and a Faust file for the audio effect chain, and of course, you know, since it takes a Faust file, you're not limited to just one audio effect, right? You can have as many as you want. You can just daisy chain them, you know, and so for example, if you wanted to make an electric guitar synthesizer, well, the electric guitar could be implemented in the synthesizer file, you know, and then all the effects chain could be in the effects chain, which is in a different file. There is built-in sensor support, where you can do many different kinds of mappings. You can so you can map accelerometers and gyroscopes to different parameters of your Faust objects. And of course, because this is very important on those devices for real-time performances, there is low latency audio, or at least as low as we can. We do our best, you know, and I'll provide you with some data at the end of this presentation about that kind of things. So how does it work? Well, it's very straightforward. If you want to generate an audio engine for iOS, you just call faust2api in your terminal, give the iOS flag, you know, and then provide the Faust file, you know, and so if you run this will just generate an audio engine for iOS implementing the synthesizer coded in this Faust code here. The same thing is true for Android. So for Android, it's also pretty straightforward. You just use the Android flag, you know, and it's really just as simple as that. So thanks to Stéphane, we now also support all these targets. So you're not limited to audio engines for iOS and for Android. You can also create audio engines for OS X Core Audio, for ALSA, Jack Port Audio, RT Audio, Open Frameworks, as well as Juice. So in other words, all the usual Faust architectures are available here, you know, but not with the user interface, you know, just with the audio layer of these applications, you know, and so the goal here is really to allow people who know how to program in C++ or in all the programming languages that are related with the system to not have to think too much about the audio portion of their app, you know, or their program, and really to focus more on the interface, you know, and let Faust take care of everything else, basically. You know? And so the reason why we're doing that, you know, is because we have some demand from like people, for example, in the industry, especially with the startup scenes, you know, like who are interested in that kind of stuff, you know, like where they don't want to think too much about the audio portion, you know, and really focus more on the user interface part of their application. So I think it's pretty important to mention that. So how does it work? Well, that's kind of a flow chart. I don't know if you can see everything on it, but you provide a Faust code, then you have a script, and then you have two different templates, one for iOS and one for Android. On iOS, things are pretty straightforward because iOS applications can be completely coded or sort of completely coded in C++. You know, I mean, you know, you normally use Objective-C, but you can write C++ code in Objective-C. And since Faust generates C++ code, you know, it's actually very easy to integrate the audio engine generated by Faust in an iOS application because those languages are very, very compatible. Midi support is added through RT Midi, which itself connects to core Midi. So it's pretty nice because it kind of takes care of everything for you. You don't really have to worry about anything, you know, as long as you connect a device to your a MIDI device to your smartphone or your tablet, you know, things automatically become available. Same thing for the built-in sensors control, you know, and then Faust takes care of converting the Faust synthesizer into a polyphonic synthesizer object, which itself gets connected to the audio effect chain, you know, and we implement our own audio engine for at the top of Core Audio, so we're not relying on anything, you know, like Juice or Superpower, as I mentioned earlier. You know, actually, I think Stéphane coded that, and so we really have a lot of control on all these things, you know, and then this automatically gets connected to the audio inputs and the audio outputs of your device in the usual Faust fashion. On Android, things are a little bit more complicated because of Java. So, you know, a few years ago, you know, like when Android became a thing, Google decided to make Java like the main language for programming Android applications, which had some consequences for people in this community because, as we all know, Java is not so great for doing real-time audio. So the only way to achieve good audio latency, performances on Android is to code the audio part of your application in C++, while still, you know, doing all the higher level stuff in Java. As a matter of fact, if you want, you can do everything in C++ if you want, you know, like because you can actually create OpenGL interfaces in C++ on Android, you know, but not everyone knows OpenGL, you know, and those things are pretty low level. level, you know. So I think the usual paradigm is really to still keep all the user interface layer at the Java level and all the real-time audio portion at the C++ level. So at the C++ level, it's kind of the same than on iOS, you know, except that, well, we're using our own audio engine, which is built at the top of OpenSLES. So we're using OpenSLES because that's what Google provided for a very long time until very, very, very recently. So I'm not sure if they actually announced it or not, but I think they did maybe 1 or 2 weeks ago. But basically, Google is now providing a higher level library to access the audio resources on Android, which is not OpenSLES anymore. OpenSLES was this thing made by Kronos, which was targeted towards embedded device in general, and not so well adapted to smartphones, basically, and so it was not so easy to deal with it, basically, and writing code at the top of OpenSLES on Android was pretty tricky, and it kind of prevented a lot of people from actually doing it, you know, but a lot of people have been complaining about that for the past few years, you know, and unfortunately Google finally heard people complaining about it. So now there's this new API, and I forgot the name of it because it's, once again, I think it was only released last week or the week before. And this new API is much, much better adapted for the kind of stuff that we're doing in this community, which is great. Of course, we don't support it yet because it's only been available for just a very short amount of time. So, yeah. Then in between there is a JNI interface, you know, because you need to create those connections between the Java and the C++ portion of the app. So those things are actually generated using Swig. For those of you who've been using it, that's kind of the standard way of doing that kind of stuff. And then Midi support is done at the Java level, which kind of sucks in a way. But there is not really any other like good way of doing it because all the stuff you get on Android at the C++ level are relatively low level, and Midi is not really one of them. Another problem is that Midi support has only been added to Android 2 years ago, which is crazy, you know, because it's been on iOS for so many years, you know, and which means that if you're running a version of Android which is older than 2 years ago, you're not going to be able to get Midi with it, you know, and so those are, you know, limitations. We'll know that Android is a little bit behind iOS for that kind of stuff, you know, but I think it's just good to remind you a little bit about those things here. So when you generate the API with faust2api, what you get at the highest level is just this very, very, very simple thing, you know. And so here it's in C++, but in Java you essentially get the same thing, you know, except that we're not using pointers, of course. So you just create a DSP faust object, you give it sampling rates, you give it a block size, you know, you start it, you stop it, and then you delete it, you know. Like, so things are really as simple as that. Then how do you interact with the parameters of your faust object? Well, it's very simple. You just, well, you have two ways of doing it. One way is to use the name of the parameters declared in the faust code. So here you have a piece of faust code. For those of you who know faust, you know, so you have the process line. You have a simple sine wave oscillator. We're controlling the frequency of the sine wave oscillator using a numerical entry. All those things kind of get ignored in our case, you know, because there is no user interface element associated to it. But then if you want to control the frequency parameter from your C++ code on iOS or on Android, or your Java code on Android, then all you have to do, you know, is to call the setParam_value method from the DSP faust object that you just created, give the name of the parameter, and then it its value. If you don't like using strings, and if you think they are too inefficient, then you can also use the parameter ID, which is a lower level way of interacting with that. And because actually, I'll talk a little bit about that later. But when you generate a faust2api package, there are a lot of parameters that can be controlled before you generate the package. And there is an automatic documentation which is generated with the package, and that kind of tells you what parameters are accessible. It's just a PDF, where you have all these things, and tells you the parameters of the engine, and the different methods that you have access to, depending on the configuration that you chose to create the audio engine. Midi support, well, I'm not going to talk too much about it here because I think Stéphane will probably talk more about that tomorrow. But Midi support is just the standard Faust Midi support, so all you have to do is to use the Midi flag during compilation, and then you can assign Midi CCs to specific parameters, and if it's a synthesizer, you can use standard parameters names to associate them to node on, node off events, or that kind of thing. So as a matter of fact, if you want to create a polyphonic instrument, which will be MIDI compatible, you kind of have to do this thing here. So if you create a Faust synthesizer which has a freq parameter, the freq parameter will be automatically associated to MIDI note numbers. And they will be formatted automatically for you, to a frequency. Gain will be associated to the velocity, and gate will be associated to node on or node off coming from your keyboard. And those things are taken care of automatically by faust2api, so you don't have to worry about all these things. So here, for example, gate could be used to trigger an envelope generator, or something like that. So here, if I just run this code, and converting that into a synthesizer, it's going to be a bad one, because it's going to click every time I press a key, which I might want or not. So it depends. You can configure the maximum number of voices of polyphony that you want in your audio engine by using this configuration flag. You can also do it from metadata in Faust. Of course, voices are only computed when they are being used, which is very important. So basically, this is just a safeguard that you use to make sure that you don't exceed a certain number of voices at the same time. Just another word on polyphony. Of course, if you send a note off message, and in the synthesizer you're using has a tail off, so let's say it's a corpus strong, for example, it will wait for the end of the tail off, until it reaches -60 dB to shut down the voice. Of course, because otherwise that would not sound good, And I mean, those things are pretty basic, but I thought they were worth mentioning. And since those presentations are so long, I can actually talk about this. Anyway, how do you access polyphony from the API level? If you have a MIDI enabled audio engine, you don't have to worry about this because your MIDI device that you're connecting to your device will be able to control the audio engine. But you can also control these things directly from the source code. There are two ways of doing it. One way is just to use a key-on method. And so here's how it works. You call key-on, then note here becomes the note number of reference that you will use to send the key off, okay? And then the object is returning you an address as a long, and then this address can be used to access parameters on a specific voice, for example, if you want to do it. The same thing can be done at a lower level, so you can just create a new voice, retrieve the address of the voice, and then use this address to access a specific parameter in a specific voice, and then delete this voice in case you want to do this. Those things are actually pretty important because when you have those kind of devices, you know, where the paradigm that you normally have with polyphony and Midi is broken because your fingers become voices, you know, like instead of the voices to be allocated to a key, you know, like you really need to be able to say, well, this is one voice, this is one voice, this is one voice, or something like that, you know, and so that's why you have access to all these things. For the audio effects, things are very straightforward, as I said, you know, so you just have a dash effect flag that you can use. You provide an effect file. The only rule is that the number of outputs of your synthesizer has to be the same as the number of inputs of your effect, you know, and then things get very nicely wrapped up together for you. Yes. Now, yeah, as far as sensor support is done, this is the standard fast way of doing it, you know, so you can use a metadata to assign a built-in sensor to a specific parameter. So, so in that case here, we're assigning an accelerometer to this gain parameter. The first number that we have here corresponds to the axis of the accelerometer. 0, I think, is for X, 1 is for Y, and 2 is for Z. And then all these things that you have here are for mapping. I'm not going to talk too much about that because I think Stéphane will probably, well, this is all in the FAUST documentation anyway. You know, so if you're interested in those things, just go in the FAUST documentation. You know, and it's very nicely explained in it. I think it's also on the FAUST website, or maybe not. Anyway, so here is a nice overview of the API where you can kind of see all the different methods you have access to. You know, I'm not going to go through all these things because most of them are not that useful. You know, but I already talked about all the important ones. So those things are relatively well documented, actually, and so if you go on my website or if you go on the FAUST website, you'll find everything you need to know about those things, and also in the README associated to this type of stuff in the FAUST distribution. So I don't want to spend too much time talking about that. Okay, now here is a brief evaluation of all these things. So faust2api is currently used for making faust2 applications and faust2 smart keyboard applications. So we kind of rewrote a little bit faust2 so that it would use faust2api internally, and also that was kind of our first test for doing all these things. I've been working on this new Faust architecture, which is called faust2 smart keyboard. If there is a little bit of time left at the end of this presentation, I'll just I'll show it to you very briefly. You know, these things are kind of still being beta tested. They were not really been announced yet, but everything is available on the Faust distribution. So if you want to play with those things, they are all there. It's been used with this instrument that I made last year, which is called Nuance. Nuance adds pressure detection and velocity detection on the screen of the iPad just by putting FSRs, force sensitive resistors in the back of the iPad and streaming all the sensor data through the audio input of the iPad, which is pretty nice because it's only using analog technology, which sometimes is great. So it's very relatively low latency, very high sampling rates, and it works relatively well. So actually, faust2api was used to make the app that comes with this instrument. By the way, one thing I didn't say is that all these slides are actually available online. I'm not watching the online version right now, but if you want to follow the links, you just have to go to this URL. I'll put it back at the end of the presentation in case you want to note it, you know, but yeah, it's karma.stanford.edu/blah, blah, 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 blah. Okay. Okay, so if you click on Nuance, you'll be able to watch videos of it and see how it works, and get more technical details about that. I have also used it for this instrument that I also made, which is called the Blade Axe. So the Blade Axe is this weird thing, which is half an electric guitar and half an iPad. The iPad is running a guitar physical model. You can control the pitch of the sounds that you're generating using the touch screen. And then you have this system here where you basically retrieve the sound of your fingers plucking plastic plates or this front plate here, and basically use those sounds to drive the virtual strings. So it's a really hybrid approach to physical modeling. So on one side you have virtual strings, but on the other side you have acoustical excitations, which gives you a very, very deep and natural control of the sound synthesis process. And the app that is running here is using faust2api to take care of all these things, and also to implement the physical model, which is running on this instrument. And I've done a lot of concerts with it. If you click on the link here, you can see that I'm not lying and that there were actually concerts, good and bad sometimes. And so those things are pretty robust, and they actually work. Now, talking a little bit about latency, because that's kind of the important stuff when we do real-time audio, right? So for audio latency on iOS, well, things are pretty good, so we have different figures here. So touch to sound latency is the time it takes if you touch the screen, for a sound to be synthesized. So those latencies here are higher than what you expect, because the touch screen itself has a fair amount of latency, and so this is not the audio latency. That's like the audio latency plus the latency of the touch screen. The best performance that you get is with the iPad Pro. This is an iPad Pro, and I think Apple did a lot of work, at improving the latency of the touchscreen on the iPad Pro. And so here you get 28 milliseconds, which is for me, I think completely playable, but some people might disagree with that, but I think it's completely okay, and then this is the round trip latency, so this is the actual audio latency, so the time it takes for a sound to be digitized, processed, and put back in the analog world. As you can see, those things are pretty constant. I'm not really sure why we have 12 here instead of 13 here. It's probably some problems during the measurements. But whatever. Those things are sort of hard to measure very, very precisely anyway. Now here where it gets interesting. So as we all know, Android had bad audio latency for a very, very, very long period of time, but Google seriously addressed this problem for the last 2 years, and now things are actually good, So for example, on the Nexus 9, and those are the latency measurements that we get with faust2api, right? So that's not the one that you just get in general, So that's the one we actually measured using our system, And so on the Nexus 9. You can get 15 milliseconds round trip latency, which is essentially just as good as what you would get on iOS, and that's great. That's only if you use the latest version of Android, or sort of the latest version, because I think there is a newer version than this one now, and only if you use this device, So what's interesting here, is that as you can see, things got much better than what it used to be, because when I gave the presentation at the Linux Audio Conference about faust2 Android 4 years ago, what I was presenting here was more like 160 milliseconds, or sometimes 200 milliseconds, And as you can see, things got much better. And so the only problem, though, is that this is limited to the latest version of Android, and it's also limited to a very narrow family of devices. So if you have an old Galaxy S5 like this one, as you can see, this is more like 48 milliseconds. So I think there is good hope to think that maybe in 2 or 3 years, once people will have replaced their old smartphones, things will eventually get better. One thing that I want to point out, though, which is very interesting here, is that the touch latency of a Nexus 9 is kind of better than the touch latency of an iPad Air 2. So Android is kind of, to some extent, almost getting better in some cases, than what there was on iOS, which I think is also interesting to point out. One thing that I want to add to this, is that even though those latencies are strongly dependent on your block size, there is this very weird thing, on Android where you have optimized block size for different types of devices. So if you want to achieve the lowest latency on a Nexus 9, your block size has to be a specific number, and I don't remember what it is, but it's a weird number. It's not a power of 2. And so if you go on the Android website, there is a table of all the Android devices that they tried, and where they give you preferred block size if you want to achieve the lowest latency, and so those things are kind of funny, but so if you want to make a very good, effective audio engine that works with the lowest latency for all audio devices in the world, the best way to do it is just to have a lot of ifs for each devices, and with the right block size, which is kind of ugly, but you might have to do it. Future directions. Well, I don't remember what the future directions are. Okay, I remember. So future directions, well, I think we want to potentially maybe add MPE support to all this at some point, and Albert and I have been talking about those things last week a little bit, just to improve the Midi support in general for all these things. And Albert has done sort of a better job than what we currently have at having, Midi channels implemented and all these things, which we don't really have yet, and all these things, so I think we want to do some work to merge what Albert has done on this side, to what we have access to in the faust distribution for MIDI support. Maybe I think another important thing to have, would be to have a more systematic way to control all those different parameters that we control here before compilation for all the architecture files, which we kind of started to do anyway, but with it's just that, for example, until recently, if you wanted to make polyphonic synthesizers in Faust, depending on the architecture they were using, the flag names were not always the same, and that kind of stuff, So there is some work to be done on that still, and it has to be done because it is obviously relatively important. And of course, just keep adding targets, But faust2api has already been around for some time now. It's pretty stable. It's working, So I think people can really use it. Now, because I know everyone is getting tired, I feel like it's time for me to play my stupid video. So we're teaching, well, as most of you know, I guess, we have summer workshops at Karma every year. And so usually we have a Faust workshop. This year there is no Faust workshop, but instead there is this. So if you want to go to California in June, enjoy the sun, enjoy Karma, and hear about Faust, mobile development, and also 3D printing and plugging sensors to your smartphone to turn it into a weird or not weird musical instrument. This is for you. I'm very ashamed of playing this video here, I must say, because, well, you'll see why. But Julius, my advisor, said that it's I should do it, so I will do it.
Yo, I'm Romain, vive la France, I love the guts and my ex in Provence. I'm programming Faust like Mars and Roust on the the illest monkey fighting coder in the house. Yo, listen up, we got this workshop summer at Karma gonna rock non-stop. Whoa, that's right folks, your smartphones turn them into flutes, drums and saxophones with microphones, iPhones and overtones. Enrich your mind like it's on the Dow Jones. Oh yeah. We're gonna synthesize sound with DSP and integrate instruments that just the first week. Designing to pieces for iOS, Android, recompile your brain like Sigmund Freud. Yo, I'm Romain, vive la France. I love baguettes and my ex on Provence. I program in faust like Mars or Browse. I'm the illest monkey fighting coder in the house. Week 2, it's gonna get real. Ransel's gonna hit you with a steering wheel. With lasers, sensors, and 3D printers. Turn audio from beginners into winners.
Oh damn, Romain, why you call that?
I don't know, Archie, I just made that. But it's round and makes sound and it's sonically profound. It's dope me with code, I'ma go with the flow. Yeah, I'm Romain, vive la France. I love baguettes and mics and Provence. I program in faust like Mars and Browns. I'm the illest one fighting coder in the house.
Hells yeah, monkey fighters! Register on the website with my homegirl Nettie!
So, you might think this is not relevant, you know, but everything was done with open source software on Linux, you know, so including sound synthesis, you know, like all the sounds were synthesized using Faust, of course. So, so if you're interested in the workshop, I recommend you to, yeah, check that out. Yes, so I think that's the end of the presentation. Any questions? Okay, Bart. Oh, I'll start with Bart. Yeah.
You briefly mentioned open frameworks.
Yeah.
I totally missed that announcement, or that I didn't know open frameworks and Faust can.
Me too.
Right.
No, I think. Yeah, I don't think it was announced, or you know, like all those new targets were added by Stéphane like 2 or 3 weeks ago. You know, like so I don't think those things are actually, but they are working, right? Or they are.
We basically just did a kind of glue code to connect with the audio chain into open framework, and then we can plug this into the faust2api system. So it means you can generate C++ files that will connect directly to the audio chain of audio framework, basically. And then you have to develop your GUI using this set param value API and this kind of thing.
I mean, to be very honest, I taught a course 6 months ago where students, and Rahul was one of the students actually, where students, you know, like were using open frameworks and just to make applications with 3D graphics, you know, and using Faust to do all the sound synthesis, you know, and I mean, if you're good enough at C++ to deal with open frameworks, then just generating Faust, well, C++ code with Faust, you know, is relatively easy and straightforward to integrate. So what I'm saying is that if you're proficient enough at C++, basically you almost don't really need all that, you know, because it means that you're actually able to integrate those things on your own, you know. So yeah.
I have actually 3 questions. Not sure if I may ask them all. First, when Faust generates code, so for Faust and for faust2api, are there any license restrictions on the generated code?
No. So so this, I think, in terms of, and you correct me if I'm wrong, you know, but there are. So the way it works is that the license that you put on your Faust code becomes the license of whatever is generated, and then for all the architecture files, so like all the C++ code that wraps around the code generated by Faust, I think most of it is just what is it? It's GNU, GPL, or not?
Well, they have a license so that you can make commercial closed source.
Yeah.
I see. Thanks. Second question is, for these Android delay measurements, have you used superpowered or have you used
No, that's faust2. There is no superpowered involved anywhere in this whole process here.
Directly OpenGL, ES, or this, however?
Well, it's OpenGL, ES with our own layer at the top of it, which doesn't really add anything. You know, like so basically that's theoretically the same as what you. I mean, it's OpenGL, yes, basically. You know, like so, and you know, superpowered is based at the top of OpenSL, yes, as well. You know, because that's the only thing that you can use, basically. So.
Some point it was too complex, and I did something simpler. I think it was working even better. Taking the API and connecting callbacks to the callbacks.
Okay, thank you. And the third question is, you mentioned you can have Faust also compile effects, and the number of inputs of the audio effects that you compile has to match the number of outputs of the synth.
Yeah.
So I was wondering if you could also create an app with faust2api that just uses signal processing to come on the microphone signal, so with no synthesizers.
Yeah, no, of course, yeah, no, absolutely. You can totally do it. I mean, as a matter of fact, you know, you don't have to make your object a polyphonic object, you know, and so if it's not a polyphonic object and it has an audio input, then you should actually put your effect code in what I call the synthesizer code in that case, you know, and then the effect becomes useless, you know, because you only want to use that, you know, if you have a polyphonic synthesizer, basically. But if you're only using faust2api to make something that is not polyphonic, you know, then the main Faust code should be the effect code, basically. So yeah, of course, yeah.
Actually, it's not a question, but I just wanted to add that IRC channel here, meaning millions and millions of people that are connected with us, really enjoyed a lot your video. So they danced and you've been called Baguette Man, and I think it's funny. So thanks to them.
Thank you.